That means the slope of graphing. The slope on this graph is the second derivative function. So would the slope negative? So that would be here and here. These would be between 1, 3, and between this 3, negative 1. Out of those, also to know where is the first derivative negative, where y value is negative. Right? This is graph the derivative, and y value is the derivative values. So let me put where we have negative slope, negative y values is negative 2, negative 1, 1, 3. So negative 2 to negative 1 and 3. Because derivative and the second derivative are both negative. Those are the places where the y values are the derivative values, and the slope values, the second derivative value, both negative. Remember, the second derivative make it constant down, and the first derivative will only decrease. Does that make sense? So then, is that clear? Hopefully not. So then it'd be that 1 point for the interval, negative to negative 1, 1 to 1.3, because first derivative is decreasing. This is the second derivative is negative, but etc. The first derivative is decreasing and negative. So first derivative is negative, and the second derivative is negative because the first derivative is decreasing. So there we go. So that would be another point. Okay, let's see. Find x of all points of inflection. The graph and give us their answer. So like maximum or minimum occurs in the first derivative is 0 and defined and just find point of inflection anywhere that derivative is 0 or undefined and just find. So question asking us relative maximum, relative minimum. So we're the first derivative where we're defined change sign. When the points of inflection, that's second derivative. Whereas second derivative is 0 and undefined and just so in this graph the slope for second derivative. We're looking for where slope is 0 and just sign. So that would be here at negative 1. That's what horizontal means slope is 0 there. And slope change for negative opposite. That would be negative 1. And then up again 1, slope 0, and it just from positive slope negative. And then again 3. Slope is 0 and changes negative slope positive slope. So negative 1, 1, 3. Because the second derivative is 0 and change sign. Let's see. This is 2 points. One was identifying this value, negative 1, 1, 3. And so they talk about first derivative, but you talk about second derivative. You talk to the first derivative changing increase decreasing, which means the second derivative is changing negative, positive, positive, negative. So you would set up further, and they explain a little bit differently, but they'll kind of same way. And the last one. Then the f of 1 is going to be with initial condition problems. Write in f of x that involved in it. So we know that when x is 1, y is 3. Right? Our initial condition here, x1 is 3. So starting off with value 3. We're going to go from 1 to whatever value x1 is go to. Of derivative. Right? We integrate the derivative to get total change of the function. So we know if our function starts at 3 when x is 1. To figure out the change that value, we integrate rate of change, integrate derivative. So from 1 to ever. So that's defined if 4 is negative 2. That means it's a pin 4 and there's a pin negative 2. And that's what these are. So plug in 4 first. Integrate from 1 to 4. I'm going to add the area, right? So I'm going to track the area to negative. Right? So 3 plus negative 12 is negative 9. Right? I count track off at 3 and 1. Right here at 1, 3. And this tells me how much the fund value changes. And this is a graph of the derivative. So this represents change in f. It goes on 12 to the area is negative. You can't do that. Sorry. At 1, the value is 3, and then it goes down 12. This area is 12. So in f of negative 2, we're only from 1 to negative 2. From 1 to negative 2. But that's going backwards. Right? We're only from right to left instead of to right. So even though this area is below the x-axis, we're going to add it. This is kind of like going in reverse. So we're going to figure out what was it back at negative 2 that made it 3 when we got here. So they subtracted 9 from where we're here to get 3. For us to figure out what it was back, we need to add 9. Right? Just if you go back, you go right to left, area is flip flopped. Below is positive and up will be negative. So we would add that and get 12. So let's see what's that pointer. So 1 point for running the integral, 1 point for pressure. Oh, okay. So 1 point for the integral part and 1 for the whole thing. So that's really 2 points for running that. And then just 1 point for funds 2 values. So it was negative 9 and 0. Negative 9 and 12. Those would be their points. Okay, so just kind of show you the GPs is a very common type question. If you put that into 2014, that Number C on 24th test is similar to that. We filled that one in a minute. If you look back at 2012 test, oh wait, 2013. So it's 13. 2013 it was 4. 2012 it was number 3. So you can see every year like number 3 or 4. Something like that. And 2011 was 4. So there's a question like every year where they either grab the derivative and they ask you questions about function and second derivative. Does that make sense? So keep in mind that when you're looking at graph of derivatives, y derivative values, slope are derivative values, and if you want to know function values, you have to integrate up to the area to get the function values. Right, the slope derivative, second derivative, y values, the first derivative here. Okay, let's see here. So this is 22 number. This is another type of one that you'll see every year. You have Fremont and all the Riemann table and asking about tables. So I'll go tell you which one in the other year like this. So, but we'll get this one. So the table here shows time, minutes, and the water temperature in degrees Fahrenheit. So this is the temperature of water at time T is modeled by strictly increasing twice different voltage values. So even though you're all seeing part of temperatures, there's letting you know that the temperature is always increasing. There's not a point in where it went down and back up. That's straight increasing. And twice different voltages that are center of existence. So it's kind of like disclaimers that they're trying to do with weird question or thing. Where D is measured in degrees Fahrenheit in 2 minutes. Time equals so the temperature of the water is 55 degrees. The water is stayed for 30 minutes, and it'll show it the first 20. They get time equal. Value W gets the time of this 20 minutes you're going to take above. So this is the data tape to estimate W prime 12. Computations of each answer using unit and treatment of your answer in the context is clone. So 12 is to be between 9 and 15. And W prime as well means the derivative of W12. Now you're trying to say derivative from a table, what you're going to use is slope formula, right? Because the derivative means slope. If you don't have any equation or a graph to find the exact slope from, like you're doing a table, and we just estimate slope using slope formula. So we would do y2 minus y1 over x2 minus x1. We would slope formula. Right? Slope is the way to calculate a derivative. Right? There's an x for lines, it's line constant slope. So you find derivative of a line using slope. But if you know approximate slope rather than systems, you still use. So it would be our y, 67.9 minus 61.8 over our x is 15 minus 9. We're using 9 because the two values close to the one that is above. This is about 12. 12 is on the table, so we're going to use two values close to it. And this is calculator pointing out these calculated in the first two problems. That's two problems. If I were to type this in, I would get 6.1 over 6, which is like 0.01. And the units would be, right, the units would be the units y over the units of x, because we did the change in y of change x, would be degrees Fahrenheit per minute. This would be the rate of change of the temperature. Rate of change of temperature at D equals 12. So every year they're going to approximate a derivative in the tool. And when you do them, you see on a single of them. And it's one of the things they could do. That just means you use the formula. I'm going to want to show you put into the formula and make them 3 units. And they may or may not be interpreted, but most of them they will. So let's see. This is the 12. Let's pull it up here real quick. On 2012 test, and 1 point for the estimate, 1.17 and 0.16. The water temperature is increasing at over approximately whatever per minute at T equals, so yeah, so the rate change of water temperature. Alright. Part B, use the data in the tool to evaluate an integral from 0 to 20 W prime T, using correct and interpret mean integral from 0 to 20 of W prime T. So just W prime, that's the derivative W. If I integrate the derivative of W, I'm getting W, right? Because we're a derivative and integral, they cancel each other out. So basically, this is if you integrate the derivative W, you'll get W. And you put the top number minus the bottom number. So we would W of 20 minus W of 0, which would be 71 minus 55, which would be 60 degrees Fahrenheit. And when you integrate the rate change, which is what the derivative is, the rate that the water temperature is changing, you get a total change, right? There's a total change in the temperature of the water from 0 to 20, the first 20 minutes. You integrate the derivative, you get function, and we have function value to say here, W of 20 is 1, and W of 0 is 55. You subtract what you're finding is the total change in the temperature of those 20 minutes. We get 15 degrees Fahrenheit, and this is the total change water temperature from T equal to 0 to equal to. So if you grade derivative, get the function. The main thing you should know it there. So this one is worth point. 1 point getting 16, and 1.4 saying water temperature has changed 16 degrees from 0 to 20. 16 degrees when it was. Alright, part B, 0 to 20, average temperature of the water in the tub is 120. The interval 0 to 20. That's the description, right? So the average, which are going to divide 20 to 20 minutes. You left 3 months out of 4 settlements, and it's about data the table to approximate this. As the approximation, estimate or underestimate the average temperature of water to do 20 minutes. Alright, so we use the left 3 months to calculate this interval. So we're going to do 0 to 4, which is the width of 4. 4 to 9, which is the width of 5. 9 to 15, which is the width of 6. 15 to 20, which is 5. And we're going to do last from, so we use the high and the left. So we're going to do 4 times 55. 4 times 55. 5 times 50.1. 6 times 51.8. And 5 times 57.8. So we're going to 12.8. And we use the 3 months sum. We have 1/20 of 12.15. If I do 4 times 55, 5 times 57.9, 6 times 60.8, 5, 6, 7.9, add the value by 12.8. And so I'm doing average temperature, I have to divide by 20. Or divide by 20. And I'm going to get 2.79 degrees. So that's the approximation overestimate or underestimate the average temperature. It's going to be an underestimate. And the reason is because the function that working is strictly increasing. If I use the left arm on increasing function, you can imagine what it looks like it's increasing. It looks something like this. If I use the left arm, I use the height of left to draw rectangles, always going to be drawing a thing that is under the curve. There's always going to be not enough area if it's increasing. If it's an increasing function, you use left arm, then any approximation you get will be under limit. If it's increasing and you use the right arm, then any approximation you get will be over limit. And then it's the opposite for decreasing. If it's increasing, left arm would be too much, this arm would be not enough. So it's going to be under limit. Left arm arm. Always underestimate. Increase arm. Alright, so then part D, it says 20 to 12, so that's 5 minutes after the end of the table. The function W that most of the water temperature has first derivative given by, and it gives a description. Based on model, temperature of water at time equals 25. So we know that after 20 minutes, water temperature is 70 degrees. So we're staying on at 7 degrees. And if I integrate from 20 to 25, because it's 71 degrees at 20 minutes. Now I want what it's going to be at 25 minutes. So I'm going to start 1. That's the start I either have. And I'm going to 25. And we grade the rate of change at the total change. So we integrate the function here, rate of change in. That's the water temperature changes the next 5 minutes. So I'm going to use it. Let's see where we're going to. We are going to type in C1. In the interval, there's a couple places you can find. I'm going to go to menu and calculus. It's 2. Or if you go to tip menu, in the very bottom row, it's second at the bottom. So either choose it. 25 of 0.4. The root of. Use the sphere as equal to cosine 0.06 t. If you don't get it, maybe your calculator on any must do this. I'll make sure both of them they're all set gradient. You don't need to agree with like it's not set to mode. Go to document. Yeah. Press the box key throw them to key and go to save the status and save region. Oh, let's get a sticker here. Good. Then I have the answer. Maybe it's what in note in my zooms are on those. Is it penny 84 times it right? Did you have any 3.42? Oh. Yeah, I'll make sure they're right mode. Or the A exam, but you want to gradient mode, so it would be actually have wrong here. Apparently, I'm not going to agree. Even the anti-limit, 3.043.